Okay, here we go into our biggest series parallel circuit to date. This is extremely similar to the one that you have in homework. So without watching this, you're going to wing it. If you run into problems, you're going to look at this problem and review it. It's 7-8 slides long and very informative, very interesting. Here's a circuit that's definitely series parallel. They want you to find the voltages at point A, B, C, and D. Now, to find those, you're typically going to have to find all the voltages and all the currents in this circuit. That's what I'm going to do. You might choose to not in this particular case, but I'm going to find them all for you to show you how they're done. And then we're going to find out what exactly is VA with respect to ground. If you look at point A, VA without a second designator always is referenced to point ground. Well, you know, VA happens to be 50 volts and we don't have to calculate anything. So now we're left with 3 problems to do in this circuit. It's a good sized circuit. It's a fairly complex circuit. The second thing you're going to be computing is VB right here, VB. Well, VB is just the sum of these 3 resistors. So VB is VR2 plus VR3 plus VR4. So you have to go find those 3 voltages. VC is a little quicker. It's VR3 plus VR4. And finally, VD. Well, VD is really just VR4. Whatever that resistor's voltage is, that's what your answer will be. Okay? Now, I'll say a few things about this slide too. You'll notice that resistor 5 and 6, they're directly tied to the resistance in this circuit that we're going to be measuring, because that resistance is going to help us get the total current in the circuit. So, that being said, 5 and 6 are going to stick around until almost the end as we move through these slides, and we're going to be compressing from the outside, looking in. Okay? The other thing is, once we're done, we'll be able to sum the voltages around the loop. And if you've forgotten what that means, we're talking about taking this voltage and this voltage and this voltage and this one and adding them together to get 50 volts up here at the top of the circuit, to get 50 volts. We're talking about adding this voltage to that voltage and getting 50 volts. We're talking about being able to go through here and around here and grab those 3 voltages and get 50 volts. That's assuming we do a good job. We're talking about going through this loop and down this channel and adding those voltages, and those 3 resistor voltages should add up to 50 volts. Okay? This is how you check your circuits to see if you're right or wrong. Most of it stems from the calculation of RT circuit that we started with back here. That 10.1, that 10 milliamps of current does travel. Let me put my marker back on. It does travel here and travel back into the battery. But you see, it splits. There is no resistor in this circuit that gets the full total current. Without that, you're in trouble. So, I'm going to try and help you out here the best I can. and keep showing you full schematics up at the top, our first goal is to shrink the circuit and make multiple drawings. We'll probably need 3 or 4 drawings to finish this circuit off. And we're going to be starting from this perspective right here and looking into the circuit. The meter is on the left. We're compressing from the right. So, making the next drawing, drawing number 2. We notice that R1 and R2 are in series. And if we add them, we get 3K. Cool, cool. We also notice at the bottom that the 2 resistors at the bottom are also in they're in series as well. So we've got 7 K ohms. That's a good start. That's a good start. The original, that puts us in position to take a look at our 7K and our 3K back into the original circuit, but a little bit smaller, So my question to you now is, looking at R12 and R6, what is this relationship here? Do they touch at the top? Yes. Do they touch at the bottom? Yes. They must be in parallel. Okay? They must be in parallel. If you compute 6K and 3K, your answer is 2K ohms. And I suggest you practice making that calculation. Now, since the top and the bottom are mirror images of each other, R3, 4, and R5 are also in parallel. They're also in parallel. Their values are a little goofier, so we would do 5K times 7K over 5K plus 7K, and we get 2.92 K ohms if we sit there and compute that. Now, what does that give us? What does that give us? If you take a look at the drawing known as drawing number 4, and I want to warn you, we're going to use drawing number 1, 2, 3, and 4 again as we reverse through the circuit backwards to solve for all the voltages and currents. So now that I've combined everything on the top and everything on the bottom here of the circuit 3, we've got R1, 2, and 6 of 2K and 3, 4, and 5 of 2.92. And finally, we get to combine those two into 4.92 K ohms. Very interesting. Ohms, 4.9. There it is. Show you split. Back here, down at the bottom. Okay, see that? We already looked at. We are at the end of our circuit here, and we've got one resistor, 4.92 K ohms. That leads us into the computation of total current, which is sitting there before you. And total current goes back to the battery, and total current leaves the battery as well. 10.162. Now, I want to notice, so keep that in mind moving forward. Now comes the fun part. We need to reverse engineer the problem. We just generated 5 drawings. Again, your arch nemesis in this process is going to be, can I reverse engineer the problem once I get RT and find IT. Can I reverse engineer the problem? The way to reverse engineer the problem is to not take circuit 5, because we've done everything we can with circuit 5. It has one resistor, one voltage. And we step back to circuit 4. Now look at circuit 4 over here. This is the circuit that we have been looking at. So I'm just redrawing it here for you. And what we can learn from this drawing is we can discover what the voltage is of those two resistors that we see sitting there. Now, those two resistors are not part of the original circuit. They are combinations. They are R1, 2, and 6. So they're snowballed. You can't really find a voltage there and get a whole lot out of it. So we're going to go and get the voltage using one of 2 or 3 techniques. 1, 2, or 3 techniques. Here we go. Actually, we're going to do it here. 1, 2, or 3 techniques. All right? And you're welcome to use any technique that works. For 126, for V126, I'm going to use voltage divider here, and I'm going to run the computation and get 20.35 volts. That's the voltage across those 3 resistors. If I went there with a meter and made a measurement, that's exactly what I would measure. Okay? Now, the second part of this problem, which is down here. I mean, this is the only things we can do with this circuit. All we can do is find these voltages. We already know what the current is. It's 10.162. There's no need to do that. We're just solving voltages to see how it helps us. So the voltage of 345, using the voltage divider, produces 29.67 volts. Now, you didn't have to do it that way. Once you've solved 20.325, you can subtract that from the 50-volt power supply, which is right here. You could subtract from the 50-volt power supply that 20.325 and be left with 29.67, the same value I got working it with voltage divider. Oh, you don't like the first 2 choices. Well, how about we just use Ohm's law. We just have to make sure that we remember that the current we're using is in milliamps. 10.162 milliamps times 2.92, almost 3K, also produces 29.67 volts, which means, holy smokes, are you trying to tell me there's more than one way to paint a room? Are you trying to tell me there's more than one way to skin a cat? Yes, I am trying to tell you that you have learned a lot of different circuit techniques, theorems, and been shown Ohm's law, and you now have, a whooping stick in your hand, and you can do it any way that feels good to you, but you have to do it right. So we can't do anything more with circuit 4. We have everything that circuit 4 can give us, but what we're going to do is take it back to circuit 3. Here is the original circuit up at the top. We're going to take it back to circuit 3 and bring back those 2 voltages and those currents that we talked about. There they are up at the top. You can see that this resistor here that's circled in green has 20.325 volts, while this resistor has 29.67. Okay? Now, we observed that these 2 resistors here were in parallel earlier when we looked at circuit 3. So, well, if they're in parallel, the voltage of R6 should be the same, 20.325. And by observation, not by computation, the voltage of VR5 should also be 29.67. True, right? You've also got the currents flowing through here. Don't forget about that. So what's happening is we're building up our values piece by piece, puzzle by puzzle, taking it back further and further into the circuit, okay? I want you to take note that if I follow the path of this circuit along the outside here, I'm going to use yellow. If I follow the path all the way around, I want you to notice that 20.325 and 29.67 adds up to 50. That tells me that I'm doing something correctly at this point. Isn't that wonderful? There's a lot you can learn by analyzing a circuit. Okay, on to greater things. Being that we now know that R6 is 20.32 volts and R5 is 29.67, we can calculate using something very simple called Ohm's law, the two currents that flow through there. We might like to know how to do that. So there it is. You take the voltage divided by each individual resistor. We now know what the current is that's flowing down here, circled in green, so that you can see exactly where things are going. So to summarize, we've calculated V6, I6, V5, I5, I total, and RT. That's quite a bit. But we're not done yet because we're only on circuit 3. We need to take our data back to circuit 2. So you can see that it's reasonably easy to follow what I'm doing because I've laid everything out for you. If you don't draw pictures, if you don't write down your equations, this could be quite a challenging section for you. So, fair warning, right? Fair warning. Now, given the information that we have there, I want you to pay attention to this little area right here. You see, you've got a junction up there. That's officially known as point A. You've got a junction up there, and that junction has 10.16 milliamps flowing in. 10.16 milliamps flowing in. And going down through R6 is 3.38. What does that mean? Where is the rest of the current going? Well, Kirchhoff's current law says that the sum of the currents is equal to the total. Well, the total is 10, and one branch goes to 3.38. That allows us to calculate what the current is going into R1. All by itself, R1. Not R12, but R1. It just happens to be that R12 gets the same amount of current as well, and so does R2. Interesting. 6.78 milliamps flows through there, and it goes, according to the yellow line, through there, 6.78 milliamps. So, into point C, if we take a look at I34 down here, we want to figure out what's going on down there. Then we take the 678 and the 338 that's flowing here, the 678 and the 593. If you combine those together and subtract out I34, you end up with 4.23 flowing through I34. Now, that might be confusing to you because it required you to know three currents right here. It required you to know three currents going into that junction. Maybe your head doesn't work that way. Well, if you take a look at what we've got, Method number 2 is just using nothing but Ohm's law right here. Right here. That'll give you the 6.78. We already know the voltage. It's 20.325. We know the resistance in the top is 3,000 up here. We know it's 3,000. We know that the bottom two resistors here, they have 29.67 volts across them. And we know there's 7,000 ohms. So that also will get you, in a quicker, cleaner way, the two currents that you needed. So, that being said, I'm going to move on and show you the whole problem here. Realistically, we have computed all the stuff that you see except for the red values. The only thing left is to go and get the 4 voltages for each of these resistors. But we just finished finding the currents right here. We just finished finding the 4 currents, and we have the resistors, so we just plug it into Ohm's law, and we get 678, 1355, 12.69, and 16.92, and all of a sudden you've essentially finished the problem, because this is what you've got. I've gone ahead and put all the values in red that we already know, and now and only now can we compute VA, VB, VC, and VD. Now VA, which is the battery right here, that sits between here and here. You really didn't have to compute anything, but if you want to, you can compute all the resistance, all the voltage, sorry, all the way around to this point. If you add 678, 1355, 12.69, and 16.92. If you add all of those up, if you did the problem right, you'll get 50 volts. You with me? Okay. Now, if you want to compute VB is going to be a little bit shorter than VA because it only goes from here to there. So you're basically grabbing these 3 voltages, as you can see right here, and adding them together to get 43.16. Okay, what else do we need to do? We need to get VC. Well, VC is even shorter than VB and VA. VC is simply the voltage from here to there, and that's 12.69 and 16.92. You get 29 volts, which we had already computed back on slide 3 or 4. I can't remember which one, but we did make that calculation. And then finally, VD is just resistor 4, because VD is found from here to here, and there's only one resistor, and that's 16.92 volts. So you've gone through the whole problem. I want you to realize that you got to make notes. You can't just watch videos. This is like being in front of the chalkboard, and you've got to take notes like you would have done in class. Yeah, I know you can go back and watch the videos, but they move quicker than you want them to move. I'm almost certain of that. One last thought. If you take a look at this voltage plus that, plus this, you get 50 volts, right? You can take any path in this circuit that you want. We can take this path. Let's go yellow. We can take this path back to the battery, and we still get 50 volts. We can take a really weird path back to the battery. Let me go here. We can take this path back to the battery and add 20.33, 12.69, and 16.92, and we end up with 50 volts. We can take any path that we wish to get back to the battery. Isn't that a beautiful thing? Let's try one more interesting path. Let's go with yellow. I could take that path back to the battery. 678, 1355, and 2967. Guess what? 50 volts. So hopefully you'll have as much success as I have and enjoy working one of these for homework.